We will start with chapter 1 on number systems. And we'll start with the definition of a number system. A number system is denoted by the symbol F. This is a set of numbers which is closed under addition and multiplication. So what this means is that if you take any two numbers, for example A and B, which belongs to a number system, then A plus B also belongs to the same number system, and the product A times B also belongs to the same number system. So the simplest number system that we are familiar with is the set of natural numbers. So it's denoted by the symbol n. This set includes numbers such as 1, 2, 3, etc., that we use for counting objects. So how do we know that the set of natural numbers is a number system? We know it from our experience. So from experience, we know that if you take any two numbers that are in the set of natural numbers, for example 2 and 3, their sum 5 is also a natural number, and their product 6 is also a natural number. So from our experience, we know that n is a natural number. Second number system is the set of integers. It's denoted by the symbol z. Z is a set which includes natural numbers as a subset. It includes natural numbers, and it includes 0, and it includes all negative natural numbers. So the set of integers includes numbers such as -3, -2, -1, 0, 1, 2, 3, and so on. So it includes all positive integers that are in the set n, and 0, and the negative of all the natural numbers, which is what we have written as negative n. So from these two number systems, we can understand this concept known as subset relation, and we say that n is a subset of z. So n is the smaller set which is a part of the larger set integers. So z is the larger set. Once again, how do we know that the set of integers is a number system? Again, from our experience, by which what I mean is that our experience in counting, we know that z is a number system. Let's take an example. Let's take two integers, say -5 and 7. Both are integers, and if you take their sum, which is 2, which is also an integer, it is a natural number. 2 is a natural number, but we know that natural numbers form a subset of integers. So if 2 is a natural number, 2 is also an integer. And if you take their product, -35, this is also an integer. So from this example, we see that the set of integers is closed under addition as well as multiplication. The next number system that we will look at is the set of rational numbers. So this number system is denoted by the symbol q. So we also know rational numbers as fractions. Q includes all numbers of the form k over n, where the numerator k is an integer and the denominator n is a natural number. So as we can see that n is a natural number, it cannot take the value 0. Okay, because we know that division by 0 is not defined. So some of the examples are numbers such as 2 over 3 or -7 over 5. These are all examples of rational numbers. Now, how do we know that the set of rational numbers form a number system? Instead of using our experience as we did in the case of integers and natural numbers, we can mathematically prove this statement. So let's try to write down our proof. So this is a proof to show that the set of rational numbers defined in this form k over n is a number system, which means these set of numbers are closed under addition and multiplication. So let's start with two numbers p comma q. in this set. So we can write P as J over M, where J is an integer and M is a natural number. Similarly, Q is K over N, where K is an integer and N is a natural number like P. So let's start with the case of multiplication. So if you multiply P and Q, so we have J over M multiplied with K over N. We know that the result is J multiplied with K over M multiplied with N. So since J and K are integers and integer is closed under multiplication, which means product of two integers is also an integer. J plus K, J times K, I'm sorry, J times K is also an integer because integers is closed with respect to multiplication. Similarly, M and N are natural numbers. So natural numbers is also closed under multiplication. So M times N is also a natural number. Okay, so we say that P times Q is in the Z by N form, which means that P times Q, I'm sorry, P times Q can be written in the form of an integer divided by a natural number. Now let's look at the case of addition. So let's do P plus Q. So we have J over M plus K over N, and we do cross multiplication to write it as J times N plus K times M divided by M times N. So here in the numerator we have integer multiplying a natural number, which is again an integer. So J times N is an integer and K times M is also an integer. And since integers are closed under addition, so if you add two integers, the result is also going to be an integer. So the numerator is an integer. And as in the case of multiplication, M times N is a natural number as we just saw. So in the denominator, we have a natural number. So once again, we see that P plus Q is in the Z by N form. Now let us do a problem. Problem 1. If Q is a rational number and if q is not equal to 0, let us show that 1 over q is also a rational number. So q is a rational number, so we write it as usual as k over n, where k is an integer and the denominator n is a natural number. And so this is in the z over n form. Q is in the z over n form. And most importantly, the problem says that q is not equal to 0. So this is an important information because it tells us that if q is not equal to 0, k is also not equal to 0. So that is an important information. Now let's consider 1 over q. So this is going to be n over k. And now it looks like we have an n over z form. So q is in the z over n form. So if we take the reciprocal, it looks like we have a number that is in the n over z form. But the important point here is the numerator is a natural number, and since natural numbers form a subset of integers, so n is also an integer, so the numerator is an integer, but the denominator as given here is an integer. So here it looks like we have a z over z form. Okay, now how can we show that 1 over q is a rational number if it is in the z over z form? So what we can do is we will consider a case when k is positive. So 1 over q becomes n over k, where the numerator is an integer, and since the denominator is positive, it is a positive integer, so this is a natural number. So what we have is when k is greater than 0, 1 over q is in the z over n form. Now let us look at the other case. Case k is less than 0. So what is going to happen when k is a negative number? So we have 1 over q equal to n over k. So in this case what we do is let's multiply numerator and denominator by -1. So we are going to have minus n over minus k. So since k is negative k is going to be positive. It is a positive integer. So the denominator is a positive integer. So it is a natural number, and the numerator is an integer, because we know that integers take positive as well as negative values of natural numbers, including and also includes 0. So the numerator is integer and the denominator is a natural number. So in this case also, when k is less than 0, 1 over q is in the z over n form. So we are not going to take the case when k equal to 0, because we have shown that when q equal to 0, as stated in the problem, k cannot take the value 0. Okay, so we see that q can only become 0 when k is 0. The denominator cannot be 0 because it's a natural number, and the problem says that q is not 0, so k also cannot be 0. So we are not taking the case of k equal to 0. So from the two cases that we have worked out, what we conclude is if q is a rational number, 1 over q is also a rational number. So far what we have seen is we started with natural numbers, which form a subset of another number system called integers, and we have also seen that integers also form a subset of another number system, rational numbers. So in a rational number, if k is an integer, and for example if n is 1, then you see that this fraction is going to be an integer, and that explains why the set of integers is a subset of rational numbers. Now let us look at if there is another number system which is larger than the set of rational numbers. So let us look at a number system larger than q. So for this concept, what we will do is try to think of the numbers as solutions of equations. So let us start with an equation like 3x plus 2 equal to 0, and we know that the solution to this equation is x equal to negative 2 over 3, which is a rational number. Now let's try to modify this equation a little bit and see what happens. Let's consider x square minus 2 equal to 0. So how do we solve this equation? So we have x square equal to 2, so we bring the 2 to the other side, and then you take square root on both sides, so you get x equal to plus minus square root. So this number that we have, plus minus square root 2, is not a rational number. So square root 2 is an irrational number. Which means that we cannot write it in the 0 over n form. Let's look at another example, a geometric problem. Let's take a circle with the diameter d, and then let's ask ourselves what number x, when multiplied with the diameter of the circle, gives us the circumference of the circle. So we will have to solve the equation x equal to c by d. We know that the circumference of a circle is 2 pi r and the diameter of the circle is 2r. So this gives us the answer x equal to pi. It is also an irrational number. And one more example for an irrational number comes from solving this equation. Natural logarithm ln x equal to 1. This gives us the answer x equal to the number e, which is a mathematical constant, which is also not a rational number. So this is also an irrational number. So now that we have seen that there are numbers that are not rational numbers that cannot be written as fractions in the z over n form, we arrive at a larger set of numbers called as real numbers, denoted by the symbol capital R. So the definition of real numbers is it is a set that includes all numbers or all points on the real number line So the real number line is just an infinite straight line going towards negative x and positive x. Infinite straight line. So if you take the set of real numbers and we remove the rational numbers from that, we arrive at the set of irrational numbers. From this we can also see that rational numbers form a subset of real numbers. So which is what we wanted to understand, that is there a number system that is larger than Q, and we have found out that there is such a number system, real numbers. The set of rational numbers form a subset of real numbers. Now let us do another problem. Problem 2. Which of the following sets form number systems? Which of the following sets are number systems? So the first case is set of all odd natural numbers 1, 3, 5, etc., and set of all odd integers including the negative numbers, and the set of all even natural numbers 2, 4, 6, etc., and the set of all even integers, -4, -2, 0, 2, 4, and so on. So the question is, or the problem is, we have 4 sets of numbers. Among them, which ones are number systems? By number systems, what we mean is that it's a set of numbers which is closed under addition and multiplication, which means if you take two numbers from this set and if you add them or multiply them, whether the result is in the same set or not. Let us consider the first case, odd natural numbers. For example, two odd numbers, let's write them as 2n plus 1 and 2m plus 1, so that these two numbers are odd natural numbers. And let's add them, 2n plus 1 plus 2m plus 1, and we will see that we are going to get 2 times m plus n plus 2, which is an even number. So this answer that we got is an even number, which means that the set of all odd natural numbers is not a number system, because if you add two such numbers, the answer is an even number. And since n odd is a subset of z odd, since in this smaller set there are examples which shows us that two numbers from this set does not belong to the same set when you add them, so which means that the larger set also has the similar property, which means that z odd is also not a number system. Now let's take the other case, n even. For example, these are two numbers, 2n and 2m, and if we add them, 2n plus 2m, you get 2 times n plus m or m plus n, which is also in the same set, n even. Similarly, if you multiply these two numbers, 2m times 2n, you get 2 times 2n or 4 mm, which is also an even natural number. You can try this case by looking at negative numbers. For example, see, we have shown that n even is a number system, but how do we show that z even is also a number system? For that, let's consider negative natural numbers, negative of natural numbers. So for example, we take uh, 2n and 2m or negative numbers, so that we can say that 2n and 2m belong to z even, and then you add them, you get 2 times m plus n, which is also negative, but more importantly it belongs to z even. And if you multiply these two numbers, two m and 2n are negative numbers, so their product is going to be a positive number, which is also an even integer. So what we have seen is examples. N odd is not a number system, so z odd is also not a number system. N even is a number system, and z even is also a number system. So is there a number system that is even larger than the set of real numbers? Yes, and we have such a number system, complex numbers. Denoted by the symbol capital C. So to understand complex numbers, let us try to find the solution of equations such as x square plus 1 equal to 0. This gives us x square equal to negative 1, x equal to plus or minus square root of negative 1. So square root of negative 1 is what we denote as I. So this number is an example of a complex number. So in general, complex numbers form a set denoted by x plus iy, where I is square root of negative 1 and x and y are real numbers. So in terms of the subset relation, we have n is a subset of integers, natural numbers form a subset of integers, and integers form a subset of rational numbers that form a subset of real numbers, and real numbers form a subset of complex numbers. There is a concept which we need to discuss. It is called as order in a number system. The concept of order in a number system. So if you take any two numbers that are natural numbers, integers, rational numbers, or real numbers, we can tell one number is either greater than another number or smaller than the other number. So if you take any two numbers a and b that are in n, z, q, r, then we can say whether A is greater than or equal to B or A is less than or equal to B. Okay. However, there is no concept of order in complex numbers. If you take two complex numbers C1 and C2, then we cannot say that what is this? We cannot say that C1 is greater than or equal to C2 or C1 is less than or equal to C2. So this ordering is not possible in among complex numbers. So that is one of the major differences between the complex number system and the other number systems, such as the real number system that we just discussed.